AI model, ERP integrated modules powered by AI. Pradeep K. Suri, author, researcher, consultant, and AI/ML architect. This AI-powered ERM system integrates legacy organizational structures, AI-driven automation, and role-based workflows for improved efficiency and decision-making. Python program to model this AI-powered ERP system. It could include role-based data access control, AI-driven recommendations for process optimization, integration with structured legacy data for predictive analytics, a Sankey diagram for workflow visualization, analysis, transcription, and detailed explanation for top and middle management, AI developer, and architect. 1. Transcription of the diagram. The diagram represents an organization structure, configuration, which is an entity relationship model, ERM, integrated with AI-powered modules for organizational configuration. Key elements in the diagram include control mechanisms, database objects, indexes, sequences, views, synonyms, roles and input/output flow, user interface programs and database objects, organization structure and definition modules. The process flow is depicted in multiple blocks, showing how data flows through various levels of control, rules, and mechanisms before defining an organization's structure. 2. Analysis of the diagram. Key components. 1. Start point. The process begins with the definition of organizational structures, which are inputted into the system. 2. Control mechanism. At each stage, there is a control mechanism governing the flow of information and ensuring data integrity. Control is linked to user interface programs and database objects, which help retrieve and manipulate data. 3. Definition and role processing. The organization is structured into different entities, which follow defined rules. Each role, such as admin, manager, developer, is assigned specific responsibilities. 4. Geographical nodes. For multi-location organizations, a dedicated geographical module is present to manage distributed teams or multi-branch organizations. 5. Database mechanism. The system maintains key database objects like indexes, sequences, views, and synonyms to manage performance and data relationships effectively. 6. Final output. The final structure is generated and configured based on these inputs, controls, and role-based mechanisms. 3. Detailed explanation for different roles. A. Top management, CXOs, directors, and senior executives. Role in the system. Decision makers, define and approve high-level organizational structures, policies, and goals. Data consumers, use AI-driven reports and insights to analyze organization performance and strategic alignment. Authorization and control, grant access to middle management and AI developers for executing policies. How AI assists them. AI predicts organizational trends and suggests optimizations. Automates workforce planning and role assignments based on historical data. Provides real-time dashboards and KPIs for decision-making. B. Middle management, department heads, project managers, team leads. Role in the system. Implement policies and strategies set by top management. Manage operational structures like departments, teams, and geographical units. Ensure role-based access to system modules. How AI assists them. Workflow automation, AI automates approval processes and resource allocation. Performance monitoring, AI analyzes department efficiency and provides actionable insights. Predictive analytics, helps in forecasting project risks, employee workload, and productivity trends. C. AI developer, AI engine developer, data scientist, AI engineer. Role in the system. Develop AI models to optimize organizational structures and workflows. Integrate machine learning algorithms for role-based access and automation. Ensure the AI-powered ERM system runs efficiently and provides accurate recommendations. How AI assists them. AI self-learns from organizational changes to improve future predictions. Helps in NLP-driven automation for HR, finance, and IT workflows. Provides automated debugging and system alerts for anomaly detection. D. Architect, Enterprise Architect, System Designer, AI System Architect. Role in the system. Design the architecture for integrating AI modules within the ERP system. Ensure that database objects, indexes, views, synonyms, are optimized for performance. Collaborate with AI developers to fine-tune machine learning models. How AI assists them. AI recommends optimizations for system architecture based on usage patterns. Automates performance tuning of database queries and indexing. Ensures high availability and scalability of the system by monitoring real-time performance. Conclusion. This AI-powered ERM system integrates top management strategies, middle management execution, AI-driven automation, and architectural efficiency to create a dynamic, data-driven organization. Each role contributes to the automation and optimization of workflows, improving efficiency, decision-making, and scalability. How legacy organization configuration systems help AI modeling. Legacy organization configuration systems have been traditionally used to structure roles, hierarchies, workflows, access controls, and data governance. While these systems were rule-based and static, they serve as an essential foundation for AI modeling. Below are key ways in which legacy systems help in developing AI-driven organization models. 1. Structured historical data for AI training. How it helps AI modeling. Legacy systems contain years of structured data about roles, departments, and workflows. AI models can train on past patterns, detecting inefficiencies, and predicting optimizations. Example, AI can analyze previous organizational changes and suggest optimized hierarchies. AI use case example. AI can study past promotions, employee performance metrics, and retention rates to suggest ideal career progression paths for employees. 2. Well-defined organizational rules and policies. How it helps AI modeling. Legacy systems encode company policies, role definitions, and process flows. AI can use existing business rules to automate decision-making and recommend policy changes. Example, AI can detect conflicts in authority when restructuring teams. AI use case example. AI-driven HRMS can automate job role assignments based on historical rules, reducing manual configuration errors. 3. Workflow optimization and automation. How it helps AI modeling. Legacy systems define business workflows, which help AI models identify bottlenecks and inefficiencies. AI can recommend automation for repetitive processes based on historical delays and inefficiencies. Example, AI can analyze approval processes and recommend faster approval paths. AI use case example. AI-powered ERM can analyze expense approval times and suggest automation rules to reduce turnaround time by 30%. 4. Role-based access control, RBAC, training for AI. How it helps AI modeling. Legacy systems contain detailed access control policies based on roles and responsibilities. AI can use this structured data to enhance cybersecurity, fraud detection, and access monitoring. Example, AI can identify anomalies in access patterns to detect potential security breaches. AI use case example. AI-driven access control can flag unauthorized login attempts based on role-based access history. 5. Legacy data for AI-driven predictive modeling. How it helps AI modeling. AI can use historical workforce performance data to predict employee attrition rates, project success probabilities, and budget overruns. Example, AI can predict which departments are at risk of high turnover based on past employee exits. AI use case example. AI can predict which employees are likely to leave in the next 6 months and suggest retention strategies. 6. Enhancing AI-driven decision-making with legacy insights. How it helps AI modeling. AI systems need legacy knowledge to make accurate data-driven recommendations. Legacy systems provide the organizational memory AI needs for better forecasting and strategic planning. Example, AI can predict future revenue impact based on historical project success rates. AI use case example. AI can simulate different organizational structures and recommend the best one for higher efficiency. 7. AI-powered data migration from legacy to modern systems. How it helps AI modeling. Legacy systems often contain non-standardized, siloed data. AI can automate data migration and clean up inconsistencies when transitioning to cloud-based AI-driven systems. Example, AI can autocorrect old inconsistent job titles and align them with modern industry standards. AI use case example. AI automates data standardization when migrating HR records from legacy databases to AI-driven platforms. Conclusion, the legacy AI integration bridge. Legacy systems provide historical data, well-defined structures, and workflow logic, which help train AI models for better automation, decision-making, and optimization. Instead of replacing legacy systems, AI can enhance and modernize them, leading to a hybrid intelligent organization. Management and AI architect perspective on AI-powered ERM integrated modules, Sankey diagram. 1 Overview. This Sankey diagram represents an AI-driven enterprise resource management (ERM) system. It illustrates the flow of processes from initiation to final output, integrating multiple organizational components. The purpose of this model is to show how AI enhances ERM by optimizing workflows, automating decision-making, and improving efficiency. 2 Explanation for management. Key takeaways for top management. Strategic visibility. The diagram provides a high-level view of how different modules contribute to the final organizational output. AI-driven efficiency. Each module benefits from AI automation, reducing human intervention and increasing accuracy. Optimized decision-making. AI enhances control mechanisms, improving compliance and performance tracking. Geographical and structural insights. AI-driven models help analyze regional performance, resource utilization, and workforce distribution. Role-based processing. The model defines clear accountability across different roles, ensuring smooth operations. Process breakdown for management. 1 Start. Initial business inputs, customer data, market trends, organizational policies. AI identifies key performance indicators, KPIs, for monitoring. 2 Control mechanism. AI regulates workflow with predefined governance rules. Helps in risk management and compliance tracking. 3 Database objects. Data from finance, HR, operations, and supply chain are structured. AI performs predictive analytics for better forecasting. 4 User interface, UI. AI optimizes user interactions by providing personalized dashboards. Chatbots and virtual assistants improve employee experience. 5 Geographical nodes. AI analyzes regional performance metrics and identifies optimization opportunities. Helps in resource allocation and distribution planning. 6 Organization structure. AI helps in organizational hierarchy mapping and team collaboration insights. Supports HR planning and workforce analytics. 7 Roles and processing. AI defines role-based access to ensure data security. Automates task distribution based on skill matching. 8 Final output. AI-powered reports and insights for strategic decision-making. Optimized resource allocation and efficiency improvements. 3 Explanation for AI/ML architect. Architectural key focus areas. AI model integration. AI/ML models assist in predictive decision-making across modules. NLP-based chatbots enhance user interactions with smart queries. Data flow optimization. Data lakes and pipelines ensure real-time processing of structured/unstructured data. ETL, extract, transform, load, processes refine data for analytics. Machine learning applications. Predictive analytics, forecasting demand, risk, and resource needs. Computer vision, automating quality control in manufacturing. Natural language processing, NLP automated document processing. Security and compliance considerations. AI-driven anomaly detection for fraud prevention. Role-based access control, RBAC, to prevent unauthorized data access. Integration with legacy systems. AI-enabled APIs bridge modern AI capabilities with existing ERP solutions, SAP, Oracle ERP, etc. Ensure seamless migration from legacy systems to AI-powered ERP. 4 Business benefits of AI-driven ERP. White heavy checkmark improved efficiency, AI reduces human errors and enhances automation. White heavy checkmark data-driven decisions, AI-powered insights help in strategic planning. White heavy checkmark cost optimization, AI-driven analytics help cut unnecessary expenses. White heavy checkmark better customer and employee experience, AI-powered UI/UX streamline operations. White heavy checkmark scalability, AI ensures adaptability with business growth. Final thought. For management, this model ensures better decision-making and operational efficiency. For AI architects, it provides a scalable AI-driven ERM framework that integrates ML, NLP, and predictive analytics for enterprise-level automation. The Deep Neural Network, DNN, diagram represents a fully connected neural network with multiple layers. Below is a detailed explanation of its components. 1. Network structure overview. The diagram showcases a deep neural network, DNN, with 5 input nodes, 3 hidden layers, 3 output nodes. Full connectivity, every node in one layer connects to all nodes in the next layer. 2 components of the diagram. A. Input layer, leftmost layer. The first layer consists of 5 neurons, orange circles, labeled input. This layer represents the input features to the neural network. Each neuron takes a single feature from the dataset. These inputs can represent numerical values, like stock prices, sensor readings, or pixels in an image. B. Hidden layers, middle layers. There are 3 hidden layers in the network. Each hidden layer consists of multiple neurons. Neurons in one layer are fully connected to the next layer's neurons. These layers perform feature extraction and transformation through activation functions, such as ReLU, sigmoid, or TAN. The diagram labels them as hidden. C. Output layer, rightmost layer. The output layer has 3 neurons labeled output 1. These neurons represent the final predictions of the network. The number of neurons in the output layer depends on the type of problem. Regression problems, example predicting house prices, rightward arrow 1 output neuron. Binary classification, example spam detection, rightward arrow 1 output neuron, with a sigmoid activation function. Multi-class classification, example image recognition, rightward arrow multiple output neurons, with a softmax activation function. 3 connections between layers. Cyan-colored lines represent connections, weights, between neurons in adjacent layers. These connections define how information flows through the network. Each connection has a weight parameter that is learned during training. The more neurons and connections, the more complex patterns the model can learn. For legend, right side. The trace lines, trace 0 to trace 17, on the right represent different edges in the network. Each trace corresponds to a set of connections between layers. 5. Interpretation. This DNN structure is fully connected, meaning each neuron in one layer is connected to all neurons in the next layer. The deep nature, multiple hidden layers, helps the network learn complex patterns. Increasing hidden layers and neurons can improve learning capacity but may lead to overfitting if not managed properly. 6. Application of such a DNN. Image classification, example recognizing handwritten digits. Natural language processing, example sentiment analysis. Predictive analytics, example stock price forecasting. Medical diagnosis, example detecting diseases from medical scans. 7. Summary. 5 input neurons rightward arrow take raw input data. 3 hidden layers rightward arrow extract features and transform data. 3 output neurons rightward arrow provide final predictions. Fully connected architecture rightward arrow every neuron is connected to the next layer. This visualization provides an excellent high-level view of a deep learning model, showcasing the complexity and structure of a deep neural network, DNN. Thank you.